to not just discuss Chicago, but talk about composting in general. No specific technology, but just everybody needs to be composting. I'll preface this whole presentation by stating that what you're going to see took over 2 years to put together with studies and presentations to our own staff, and the conclusions that are made are site specific. So I always like to start with that. I'd like to acknowledge my co-author, Matt McGregor, who's a principal civil engineer at the Water Reclamation District in Chicago, as well as a team of staff from around the district, soil scientists, accountants, and other engineers as well. So a little bit about the district. We're pretty large. We generate 140,000 dry tons of biosolids every year. Today's focus is going to be a little bit on Stickney, but pretty much the technology evaluation and strategic planning for the Calumet plant. So without further ado, I'll jump right into how we process our biosolids. We do anaerobic digestion, and from there, the 3 to 4% solids goes to a lagoon for further stabilization, and that low salt product later taken out of the lagoon at about 8 to 10% solids, put into a semi-tractor trailer, brought to a drying bed where we mechanically agitate it to 60% solids, and then load it out to a farm, either at 60% solids, or in the spring and fall, we typically will stop around 35% solids and ship it out to farm. If we decide to test it, because we have a call for Class A, we'll do that, screen it, and get it out. Now, as far as centrifuge cake goes, we have a portion of our material that goes there. From there, it comes out 22 to 25% solids, depending on the time of year. And we do have our own railway, which hauls the biosolids cake to our lagoons. So Stickney and Calumet combined have 18 low solids and cake lagoons, totaling near 4.5 million cubic yards of storage. This picture just shows our train car dumping our centrifuge cake into a lagoon and waiting for future utilization on a farm. So all winter long, we're storing it. We don't have a permit to haul to frozen ground, so we hold it in the winter and start loading it out in the spring. As far as the drying process goes, we have 7 drying sites that we utilize, which total 390 acres, and we process 90 to 100,000 dry tons a year. So the sites all look pretty similar. They're sloped in such a manner that rain or melted snow will drain off the biosolids and go into a piping system, which leads back to the plant for further treatment. Our process is very land intensive, and we start with a booster, which pulls a rail. Basically, it's just a railroad tie through biosolids, and it agitates it, flipping it over, creating a wet surface over and over again, kind of like your hands underneath the dryer in the bathroom. The more often you do it, the faster you do it, the quicker your hands dry. When it thickens up, we then agitate it with a tractor and a rotavator, which is just a farm piece of equipment. It tosses the material up in the air. It's very quick and efficient, and when it gets a little bit thicker, or we need to get all the way down to the pavement, we then employ a brown bear, which is the lower left-hand corner, and then at 60% solids, we'll stockpile it and get ready for shipment. The district has been utilizing its biosolids on farms, its Class B, for over 30 years. It's an award-winning program, and we've also been utilizing Class A biosolids around Chicagoland now for quite some time. And we use it on athletic fields, golf courses, and other parks and recreational facilities. One of my favorite areas I worked at for 3 years was the Harborside International Golf Course, where they utilized biosolids in the shaping of the entire golf course. And they capped it with 2 foot of clay, and then again used biosolids in the blend for the final growing media of that golf course, which is held to some senior PGA events. This is my favorite slide because it shows you with these little green leaves just where in Cook County and Chicagoland area we have brought Class A biosolids. This is not Class B, just Class A. So some of these green leaves are pretty far away, so you can imagine the hauling costs are pretty high. We don't charge anybody for the delivery, but we do try to get it to anybody who wants it. But that's not our only problem. So it's no secret that we all face public opposition with our programs. So it's important for all of us to address the public, listen to them, their concerns, and be proactive in helping them to see that biosolids can be a safe soil amendment to use, especially when we're talking about biosolid safety, getting people over that ick factor, heavy metal questions, and then PFAS. Our most in-depth questions come from heavy metals, which we addressed back in the 80s. So it's still an issue. So with all this in mind, we realize that we want to continually improve our program. It's award-winning, but that doesn't mean you just sit back and do nothing. As with many of you, we want to be better. So we invested some time and effort into a voluntary program of WEF called the National Biosolids Partnerships Environmental Management System. So we started that in 2000. We had a couple different leaders. It finally got turned over to me in 2006, and in 2008 we became a certified agency, and in 2018 we became a certified platinum 10-year agency. So, but what is it, and what does it do for you? An environmental management system is basically just a framework to identify opportunities throughout your plant to become better. It helps you to plan, come up with a plan of action to handle your opportunity for improvement, to carry that plan out, and to check to see how you're doing over a course of time, and then revisit your plan of action and start over again should you need to improve some more. So it helps us in major areas of regulatory compliance, getting standard operating procedures down on paper, which was a big problem for the water rec as our staff became a little bit older. You'd say, where's the standard operating procedures? And the guys would point to their head. They just know how to do things. But when they leave, how does the next guy know what to do? So it helped us with that. Our product and service quality, and then again, our credibility with our stakeholders. So we learned quite a bit from the EMS. So one of the elements of an environmental management system and how it can help you is critical control points. This particular table is called a critical control point table. And there's about 5 elements of the 17 in the program that are involved in this table alone, with operational controls, potential environmental impacts, how you monitor, and who's responsible. When the district took a look at their biosolids drying practices, we looked at different areas. And here, this is just one page of many, but you see we have the CCP of lagoons and air drying. So just looking at those, our executive director said, hey, we need to improve our odor issues and the poor quality of our biosolid, because when we ship it out as Class A, some of it is inch in size, some of it's small, it's odorous. So how do we handle all this? So we need to set goals and objectives to address that. In addition, we took an approach to look at all of the different areas of the process. So going back to this slide, everywhere you see a green star is a critical control point area where we took a look at different things and came up with goals and objectives, not for all of them, but for some of them. And from year to year, they change depending on how the budget is and what the strategic plan might face. So what the EMS did teach us is something I never wanted to address. And maybe some of you are a little more old school like me, where, if you're out of sight, you're out of mind. If you're flying under the radar, you're doing a great job. So that was kind of me. Growing up, I was taught to try not to have a spill, try not to have odor complaints, because the last thing we want to do is see ourselves in a newspaper or getting heartburn through that. But looking back, I wish we would have started this program sooner, because as we wait to address our incidents, whether it be odors or spills or anything else for that matter, the cost to address it goes up. And one example of that is where I show here that you have politicians voice concerns. We had a farmland program where we brought biosolids out to a farm in late fall. The weather changed, we couldn't apply it, and then in the spring, it rained and rained and rained. So we had to get approval from the IEPA to leave it there and not bring it back to the plant. But when we finally did spread it, it stunk to the high heavens. It turned out that a local politician lived just on the opposite side of the farm, and he was not very happy. So our public relations department did a great job getting out there and kind of satisfying the needs of the politician. We became very proactive in dealing with the media out there and we kind of stopped there. But we later used that same politician to help us pass some bills and ordinances, which we'll talk about. So address your issues early, not later, where the cost to address them can be very great. So another element of the EMS is setting goals and objectives to address the identified strategic plan areas that the executive director set. So he said, you know, Dan, let's get together, figure out what we need to do here. Biosolids, you've been doing the same thing for several decades. Let's change it up. So he says, let's add value, let's increase resource recovery around the city, and let's be a leader in partnerships. And we had to put some folks together to figure out how we're going to do all this. So one of the ways we knew we could do that is decreasing odor, coming up with a more consistent product, and then trying to get the city involved to take some of the product off our hands when we made it. So potential areas, environmental impact, were a major list, had a major list of items for us to consider. So we no longer wanted to air dry the Calumet plant. We said, you know what, let's look at alternatives. So we looked at alkaline stabilization, solar drying, composting, and even more. So we had a wide range of alternatives to look at that I was looking at, and they said, no, Dan, we want a team to look at and evaluate the different technologies, because this is a district strategic plan, not your strategic plan. So I said, okay, that's great, takes a little pressure off me. So we had a multi-departmental team made up of the finance people, procurement department, maintenance operations, engineering, and our monitoring and research. So it was a great team that took just a holistic approach at reviewing all of the technology. So it wasn't one opinion, it was many. And then we evaluated them with a modified triple bottom line approach that included different evaluation criteria, economics. The technology had criteria, had several facets to it, and then environmental and social criteria as well. Making our short list for our specific plant, the Calumet plant, was heat drying and composting, and for Stickney as well. The advantage is the heat drying was Stickney already had one, so could we build another one there? And for Calumet, it didn't have any kind of heat drying. Could we put one there? So we knew that we had good odor control. We knew that it produces a nice dry pellet, Class A, and it's in a building, so it's not subject to weather variability. And we could also have the potential to bag it and have a nice revenue. Composting has many of the similar qualities as to pelletization, but we know we can store it without having an odor issue or any quality degradation. And scaling up, should you want to scale up, is not much of an issue. If you just want to add windrows, or if you need to add systems, it wasn't too much of a big deal. So, and again, potential for revenue. So we plug air drying, composting, and heat drying into our triple bottom line analysis. It was clear to us that composting came out on top. So now that we had the direction that we were going, what do we do? Well, we knew that composting addressed 3 of the 6 main goals that our executive director set for us. It added the value. We're going to address odors through composting, and we're going to have that desirable product. Resource recovery, if we can gain wood chip and yard waste from around the city of Chicago, we're going to increase resource recovery by keeping it out of landfills. I know California has a big ordinance to keep organics out of landfills, and it's just a good idea. If you could use it, use it. So we were looking for some type of agreement with the city and surrounding communities to bring us our feedstocks. And then we wanted to lead partnerships, and composting would provide us with the means to do that, because partnerships would be an intergovernmental agreement with the city for resource recovery. And then we had the pelletization plant at Stickney, and if we could, and they wish to bag some of their product, and if we were able to have a compost product that was bagging, we could share that cost. So we were looking forward to that. Composting also addresses EMS established goals by producing a higher quality product. It reduces the overall operational cost. Basically, we use brown bears and other heavy equipment to dry our product now. And when it rains, we have to re-dry it. do it over again. So there's a lot of fuel involved, a lot of greenhouse gas involved. So we're trying to reduce our operational footprint as well as our carbon footprint, and then increase the adoption of our Class A distribution within Cook County. So if we have a Class A odor-free product, more people are going to want to use it. So one of the things that we decided to take a look at was where do we have public opposition? And at the Stickney plant, we really didn't have much of a problem. So we just chose windrow composting. We don't need to enclose it. We don't need a big system out there. Let's just start windrow composting. So that was chosen because there's no opposition to our air drying at the time. The Calumet plant, however, had other issues. I mean, obviously all around Chicago, weather is an issue, not just the Calumet plant, but Stickney as well. But we met with the local residences and some local officials that said, you know, you're creating an odor and dust nuisance for us across the street from the plant. We'd like you to do something to mitigate that. So enclosing or covering the biosolids operation was their best solution for odor and dust control. So we decided to look at composting enclosures that included in-building, covered aerated static pile, and in vessel. Composting in a building has the advantages that you can do whatever you want pretty much. You can windrow in there, you can do aerated static pile, positive or negative, but you would need a biofilter to handle the air, and then it provides the ability to reclaim the heat and treat the odors. The disadvantage is that if you build a building for a specific amount of biosolids composting, if you want to scale it up, you need to build another building. So it's really not scalable, and it was not, the present value was not cost effective for Calumet with the operation just for the building being between 60 and 70 million. And then our research team showed us that that when we made our phone calls, did our due diligence, that ammonia, formic acid, and acetic acid, which are coming off the compost, provided with corrosion risks to the building. So that was kind of an issue, increasing maintenance costs. And then with that, the potential for unpleasant working conditions. So we're trying to improve conditions, not degrade them for our staff. So covered aerated static piling, again, odors are easily controlled. It's simple operation. It has lower overall cost, and the versatility of negative and positive aeration were very attractive. So whether you're using some kind of cover, membrane cover, or you're using a wood chip or finished compost cover, you can use some negative or positive aeration, negative needing a biofilter to go with it, but you had the versatility there that we liked. The disadvantage is that with the membrane covers, you have to replace them after so many years, and with the wood chip cover, we needed a lot more feedstock, or we would have to use our finished product, which we didn't want to do. And you know, as far as labor goes, we time trying to get our operators to put a 12 to 18-inch cover over the compost and having that consistent layer there. So labor increases because now you're not only building the pile, but you have to spend all the time to cover it. So for Calumet, the executive director said, you know, wood chip or finished compost cover is not going to work, so we have to figure out how we're going to cover it. In vessel composting was exciting to me, and it uses just a mixture of the biosolids, the bulking agent, and they feed it into an enclosed container or vessel, and it's just run through there. You're adding some air, and it's mixing up, and it comes through the vessel on the discharge end. I like it because it has a small footprint, smaller footprint than a building. The process area is less than a building, and it has really good control over the composting process. So there's less bulking material required as well. As far as the disadvantages goes, they had a very high cost range from 104 to 150 million. So when we put the three technologies into a present value analysis, it was clear that composting in the building and composting with covers were very similar. So we had to really choose between the two of them. We thought that in vessel, due to the present value, was going to be too much at 282 million. But when we popped it into the triple bottom line approach, I don't need to show you the whole table there, that whole analysis. The scoring kind of evened out with the in vessel and building composting, but covered composting came out on top. So now we needed to vet this whole thing and to a team of people. So we've done our homework. Now we need to present to another team. That's how it worked at the district. So we presented to a team. They said for Stickney, okay, we understand, go with the windrow composting. And with Stickney though, you need to do an evaluation of the different covers that are available to you before you go with design and construction. You can't just move forward right now. So we needed to vet that out. So we got a couple of pilots. We received full-scale CapEx and OpEx proposals from the two different technologies. We performed a pilot with a semi-permeable membrane and a non-permeable membrane. Both of them were using positive aeration, with the non-permeable having a biofilter to handle the process air that went through the pile. Over a 6-month period, the non-permeable membrane was not successful. We couldn't meet PFRP temperatures, and we created a pretty big odor nuisance. However, the semi-permeable membrane was successful. We made several batches of Class A biosolids compost, and odors were controlled. So with the semi-permeable membrane with positive aeration, we like the fact that odors were not an issue. Just for making phone calls and doing some research, we learned that the lower energy costs went with positive aeration versus negative aeration and sucking air through the pile. In addition to that, we had no biofilter. We would have to maintain the process that we were looking at was PFRP compliant with the pilot. It also controlled VOCs and was flexible. So it had a lot of positives to it. But the short-term plan, while all this was going on, was to windrow at both facilities. So we vetted out projects to do so. And the long-term at Calumet was to come up with a covered aerated static pile, which was a 3-phase process. Phase 1 and 2 being the active aerated composting phases, and phase 3 being the cooling and curing phase, which we did what we were going to do with our windrow turners. We didn't need any additional infrastructure, and the result would be a Class A EQ compost. So over this 2-year process, the EMS led us through continual improvement, and we were working with the state legislator that complained about the odors to help us realize not all of it needs to go to Farmer B Class B, but if it is made EQ Class A, it can be regulated other than a sludge or a waste. So House Bill 1445 was passed in 2015, and that's due to our lawyers, our soil scientists and engineers that went and fought for that, and basically allows for nearly unrestricted distribution of our composted biosalt. So it's very exciting. And then in 2018, we were able to pass another House bill we worked on for state agency use. Basically, this legislation increases the use of compost for transportation projects with state agencies and helps to create a market for all compost, not just biosolids compost, but compost. So it's a win for the compost. And the agency that undertakes a landscaping project has got to look at compost as a growing media or part of their blend, and it's really helped us utilize our product. In addition to that, the district has a resource recovery ordinance now, and part of that is to receive fog, but for our concern, wood chips and yard waste are part of that program. We receive wood chips for free, and we do charge $10 for people to drop off yard waste per ton. So a summary of our program is we have a public and private partnership. So that met one of the goals. We have an IGA with the city of Chicago, and we received over 100,000 cubic yards of wood chips to date. The resource recovery ordinance, where people have to sign up to bring us product, we've received 25,000 cubic yards of wood chips for composting, as well as we receiving 5,000 yards of vegetative matter over the course of the last couple of years. Our finished compost, we've utilized to date over 90,000, it's probably well over 100,000 cubic yards of PFRP equivalent Class A compost now. We registered the product as a soil amendment in 2017, and we've applied for acceptance of it, waiting acceptance of an STA number from USCC, and we haven't received that yet. And then we sent folks to compost training back in 2019. For me, what's most exciting is after I retired, I went back for a Christmas party. They began bagging, and my former staff provided me with a nice Christmas gift of a bag of EQ compost. And then on the back of the bag that we had designed, it tells people how to use the compost. So it's very exciting. They can't keep it on pallets. And in bulk, it's used all over the city of Chicago in community gardens to grow, flowers, to grow vegetables, teach kids how to plant and harvest. It's been a wonderful program. And if you ever get to Chicago, go to Maggie Daley Park and see everything that's grown green as biosolids in its blend. So with that, I thank you, and I look forward to answering your questions later on.
Hey, Dan, thanks a lot. What a great presentation. It's great to see the transformation over the years. We do have a couple questions. The first one is, was anaerobic digestion considered as part of any alternative to reduce solids volume, thereby drying composting size needed, and recover renewable natural gas?
Yeah, that's part of their plan still moving forward. The anaerobic digestion, all of the material is anaerobically digested. I know there is a study out there right now. They're looking at bringing in fats, oils, and greases to increase the energy usage at the digesters. They currently use the gas to help offset costs for the pelletizing facility at Stickney. So that gas is not being flared 100% of the time. Most of it is being used at the pelletizing facility and for their in-house boiler system.
Okay, great. A second question, Dan, how are you addressing PFAS regulations as they develop and the implications to land application of biosolids and or compost?
Well, the PFAS has come up since I retired. So I know I've been talking to them about it. They're analyzing their biosolids. They're not finding PFAS in Chicago's biosolids. So they continue to look for it. But how are they handling it? Right now, there's nothing for them to do. And so it has not been an inhibitor to the biosolids land application process.
Okay. All right. Well, great, Dan. Thanks again for taking your time and for sharing that with us. That's all the time we've got for questions for Dan right now. I want to encourage the audience, please continue to use the Q&A feature to continue asking questions, and we'll get to them time permitting at the end of each session. I think I see that, Dan, you've stopped sharing your screen. Charles Dupre will now be presenting on the common compost testing challenges and the need for performance-based design. I'll give everyone an introduction to Charles via his bio here. Charles Dupre is the president of NatureCycle, which is a firm focused on sales and marketing of compost and engineered soils throughout New York, New Jersey, and Pennsylvania. Working with a variety of private and public composters, NatureCycle provides material for projects and retail use throughout our region. He served on the Market Development Committee of the U.S. Composting Council for 8 years, along with working to develop some of the largest green roof and engineered soil projects around New York State. Mr. Dupre has a BS and a BA from Syracuse University and resides in upstate New York. And more background can be found at his website, www.naturecycle.com. It's my pleasure, Chuck, to turn it over to you.
Thank you, Jeff, for the kind introduction. So I'm going to talk a little bit today about some research we conducted previously at NatureCycle and was published in Biocycle in late 2019, and then expand a little bit about how the basis of this research pushes towards the need for more performance-based design for soils and other applications, kind of also building upon some of the things that Chicago seems to have discovered with their own research and examination of different options. So let's see if we can scroll in here. So I'm going to briefly talk about a marketing sales type concept here. Let's call it product adoption. We'll talk about some compost testing challenges that we researched. We'll look a little briefly at the seal and testing assurance program itself, and then some common issues. So NatureCycle, a firm I founded back in 2016, focused on compost and engineered soil marketing and development throughout the Northeast. So very briefly, compost products, biosolids products, soil products all face a very similar issue. It's that if you're going to market something that isn't necessarily a simple commodity, it requires a common language. So the picture on the right kind of gives you an idea that, you know, a number of manufacturers make tires. There's different types of cars and sizes, but there's a universal language for a tire. Common things anyone can reference to be able to buy a tire from one manufacturer or another for a different type of car or trailer, anything you might need, there's a common language. So that information then lets you build a market around that. So from a consumer standpoint, those are the tools you need for repetition and ease of use. And if you have that, you have wider and wider adoption. So the Composting Council as an industry and some major players like Procter & Gamble and Kimberly-Clark in the late 90s recognized this. So if you're not familiar with what compost is, I'm sure everyone on this call is at least kind of familiar. A quick definition, it's a humus-rich soil amendment made by the controlled biological decomposition of organic materials. So just a pictured example of a compost. We'll breeze through that. So in that late 90s, this industry trade group of composters and related industries that might make a compostable product, et cetera, put together a working group that developed something called the TMECC, the Test Methods for Examination of Compost and Composting. This book of different test methods, it was culled from existing research and new research to come up with the best ways to evaluate the composting process as a manufacturing process and the finished product. So this group of scientists and researchers and industry professionals broke off into teams and looked at things like pathogens and heavy metals, looked at existing testing methodology for something that might have been applied to just a biosolids cake or to a potting media that was used in a nursery, and then put those pieces together in a document called the TMECC that was then published for peer review. Once that was published by the EPA in like 2001, that document was then available for use. Part of that document and comes out of that testing methodology framework comes two different things: the Seal of Testing Assurance program itself, which is based around the TMECC, and the CAP program. The CAP program is the lab-specific aspect of this that many of you involved in composting might not even be familiar with, but there's a compost analysis proficiency program behind all this, checking and monitoring the labs, and I'll get a little bit more into that in a second. So just very briefly, if you haven't seen an STA data sheet, this is the power of a universal language of compost or of any product like I showed on that tire. If you've got those universal standards tested the same way, presented the same way, now I compare apples to apples throughout the country. These are two New York composts, but I could have a compost made in Florida, a compost made in Chicago. The data is presented the same way, tested the same methods, and now I can look at two different materials and evaluate their use for my project or for a variety of applications. So I'm very briefly just hitting this stuff to kind of lay the groundwork. But here's where the research came in, is that although this is becoming a wider and wider standard, not everyone does it, and they're not necessarily required to do it by a federal law or something that spreads the entire country. So if not everyone is using the same standard, some issues are going to arise. So we drafted an article I ended up calling Comparison of Compost Laboratory Results, studying two different composts. The Compost Analysis Proficiency Program basically is doing the same thing behind the scenes, but only with the labs that participate in STA. It's about 12 right now, maybe 13 coming online throughout the country, that the director of this program, Dr. Bob Miller, takes split samples of compost, sends them out on a regular quarterly basis to these different labs, and does a statistical analysis to make sure they're getting results within set parameters. Well, it's beyond just the pure data analysis. It also points out that if a lab isn't participating in this program, the average user might not understand that there would be a difference. From a scientific standpoint, it's not a criticism of a lab not using TMECC or a negative on someone not doing this. It's just purely a factual understanding that if I was used to STA or was looking for standardized data, like I can find in a tire or like I can find with an ASTM, with compost and with some things about soil, that's not as readily available. So recognizing these different methods, it's mostly an end user problem we're dealing with here. So it's a lot of charts and numbers to look at on a Zoom call, but for general use, this article is also on Biocycle's website. We took one control sample, split it 6 different ways, and sent it to 6 different labs, one of which was the TMECC, A&L Great Lakes, who kindly donated their resources to do that analysis. and then 5 non-STA labs that specifically advertised as that were not in the program, did not claim to use the standards, even though they may behind the scenes. We wanted to replicate the data and look at some different examples therein. So these are actually split samples. A1 was a well-made lawn and leaf compost, and B2 was a biosolids compost product, both from the Northeast here. It's a lot of data. I'll dig down a little bit here within some of these variations. There's 3 key areas from a soil science standpoint that are most interesting, and again, kind of tell the story of that common language. There were some major variations in the pH as reported. Now, pH is a measure of any free hydrogen ion. It's a logarithmic scale. As again, many of you involved in wastewater are very familiar with this. But within the samples themselves, there were some very large variations. Some of the biosolids, the labs reported the biosolids compost having a pH as low as 7.08 and as high as 8.18. It's a huge variation from a soil standpoint of how much I might want to add or be limited to add. This relates to their methodology of testing. Again, not a bad or good thing in a judgment, but just the average user, the end user that might just be the landscaper in Florida or Chicago might not understand the differences presented to them. And these are still challenges we face in the market. Beyond just pH, soluble salts is another important one for nursery growers, for commercial growers in general. That's a measure of the free nutrients, any ions again, and that varied even more wildly potentially than the pH at times. You had some, even in the lawn and leaf compost and along with the biosolids, you had dramatic differences in results, which relates to how much of the material you could use or might want to use. TMECC has very specific guidelines on how compost should be analyzed based upon that group of guidance at the time that looked at the available research and said this is the most representative test for how compost should be analyzed and looked at based upon its uses. Compost isn't soil, compost isn't fertilizer, it's a soil amendment. You should look at soil amendment type testing and develop the best recommendations based upon that. So the last one we'll just briefly touch upon is that variation organic matter. I'll go back to the chart for just a second since we're moving along quickly. Organic matter is an important source of food for plants. I'm far oversimplifying that, but trying to give you a general concept of how these things get used. It's also one of the things that gives compost in particular its most value. Even any biosolids product, the organic matter is what you're often selling. It's that high OM percentage organic matter that the farmer or the end user is going to find most useful. So if it's a pellet or a cake material or a compost, knowing that value is very important and how much they should add to the soil to improve it, et cetera, is useful from that calculation. There was one lab in particular that was a real outlier in this scenario. Going back to this, this is another test that it's not a good or bad scenario, but the labs that weren't in STA, you can also look at the intra-lab variation was often quite different than it would be from the TMECC lab. If you look at A&L and that first report in the top left, the A1, A2, B1, B2, the variation between the split samples, so this was one large sample even split within 2 for each test just to get the replications, are very small, tenths of a point quite often. There are some variation. But within the lab, other labs that don't participate in that CAP type proficiency, having someone checking them, not all the labs, but some had some very large intra-lab variation on occasion. And when you start seeing a few percentage points difference, statistically, that's a big issue when you're trying to build programs or make decisions about how your material gets used. It wasn't true everywhere, but just something to take a look at and keep in mind when we're evaluating next steps in programs and ways we can build further. So, you know, looking at those different labs and evaluating the differences from the TMECC, it comes down to the idea again of accepted standards. A rising tide lifts all boats, especially I would think in our industry. There's still a fair amount of, let's call it differentiation in the sense that there's a lot of different regional players, regional markets. So if we have standards that improve for everyone nationwide, you know, there will be competition, but in theory, I would think objectively, we could all say it's going to benefit more of us than it would necessarily see as a negative from a sales standpoint. if we can find more universal standards. Accepting these, general standards can also lead to looking at other materials that aren't necessarily compost. If we had better universally accepted standards that focused on organic matter or end uses of these products, other things that aren't necessarily compost could also come into play. Things like pelletized biosolids or a Class B residual. They can offer a lot of the same benefits, and they could be used if that's what's regionally and local available. I'll take the next one. So that brings us to that performance-based design. We've kind of looked at what gets built around the testing and the analysis. What's the next step to that? Now that we know we can create these independent data sheets and some sort of program, be it for digestate or compost, if we have that standardized data, we can then develop what's called a performance-based design. So focusing on the ends, not necessarily the individual ingredients as we're going along. I'm again oversimplifying this, but a cake recipe is very specific. Add this amount of this product, when realistically, we're just trying to make a dessert. We don't necessarily care if it's cake. We're trying to make some sort of dessert that best feeds our plants. So maybe this time we add 10% pelletized biosolids by volume to get the increase we need in the soil organic matter, and 25% compost in the next project. We still get the results we want, but not necessarily by the same methodology. It broadens our potential uses for residuals if we can look at these things more focusing on what the finished result should be versus the individual components. Just a quick example, again, if you're in the wastewater and specification world, like everyone on this call probably is, we're familiar with specifications and designs, but from a soil standpoint, just trying to give you a general idea of that if you're looking at these programs, this is how someone might look at the end use. Just an example of what a performance-based soil design looks like. Instead of saying specifically mix topsoil, sand, and compost at 1-1-1 and mix it all together, it's saying the final blend should have X amount of organic matter or between this much silt and clay. It's really focusing on the ends, not the individual components. And then you can base it around different testing and things along those lines that are useful and specific to your job or region. What that performance-based design allows for is those regional and local differences. With what products are best and locally available to you and in that market. So even with those laboratory challenges, if you had a more common language of use, you could probably develop, or we know you could develop more useful tools and different ways to use your compost. Just like Chicago demonstrated, they went out and found other markets like top dressing turf beyond just pure farm application. So looking at the parameters of the product in a consistent manner allowed them to develop that further. And it also opens the doors to other residuals. If you're not overly specific and you're not trying to purposely keep out competition, which quite often happens, you can open the door to other residuals that might be a better fit locally or might be readily available to that particular highway project or athletic field construction. Maybe there's a small biosolids plant nearby that makes a cake material, et cetera. So in summary, that kind of talks a little bit about looking at some of the testing and the analysis we've done over time. We looked a little bit about the Seal of Testing Assurance program and how that's kind of developed over time. A little bit on our research article, which I'm glad to share with anyone after, from the biocycle in fall of November of 2019, some common issues that then come out of that testing and design, and then how a performance design can be beneficial. Glad to take any questions. We've got some more information on our website.
Good timing, Chuck.
Yes, and I had a little tiny invader. My apologies.
No worries. I think that happens very commonly in today's WebEx, the Zoom meeting environment. But great presentation. Thanks for that overview. We do have a couple of questions if we can throw them at you here. First off, with respect to soluble salts, is there a standard value for a compost or a finished product containing compost that is accepted for landscaping projects? What is this value based on? Research into soluble salt toxicity, et cetera?
Not really. It's more of a regional question than anything. In the West Coast, a landscape designer and end user will have to allow a higher level of soluble soats than they would in the East Coast. But the Compost Council has done some further research and look at some white papers to try to develop a more common range. From a true soil science standpoint, most of the stuff we deal with compost, there's not a lot of quote unquote negative salts in there unless you have a real problem. I'm far oversimplifying this. I use that phrase a lot, but I am no true expert. At the end of the day, there's good and bad salts, we'll call them for the purpose of this conversation. And most of the bad salts aren't found in most of our composts. Anything that has a free ion, those nutrients you want, like NPK, also show up. So a fertilizer is a salt in a way. It is a type of a salt. So we're looking for these things in a test, and the test doesn't always represent well which of those salts are in there are quote unquote good or bad. So I've seen compost work well with ECs of 10 or 11 and work well with an EC of 0.1. But you can also, if you have an EC of 0, I'm not sure your compost is going to have enough free nutrient to do anything. So there's a wide-ranging answer here, but it's kind of one of those catch-22s of if you think you've nailed this issue down, then good luck with that.
Okay, great. Another question. Hello, Chuck and kids, with a smiley face. How can we help promote this approach that you were outlining as far as performance-based standards? How can we improve and promote this approach?
Participating in STA is a big one to start. The more participants in programs like that, if you're producing a biosolids compost, they've even got small facilities fee. If you have a small facility, there's more participants in programs like this or similar. I know the AD folks have talked about something similar over the years. If you have a program that then we can approach state regulators about and say, now there's 10 or 15 participants in your state, you can go to them and say, these are standards we should be looking at in highway construction, in environmental work. We're doing this right now, Nature Cycle is with the state of Vermont, looking at how these things could be adopted statewide. And the Compost Council has done it previously in states like Colorado and Texas and California, supported our members in growing that acceptance. But it's a chicken and an egg. You really need participants and people building that STA participation or some sort of similar program to then be able to push that further adoption. You got to leap before look a little here.
And Chuck, are you seeing kind of maybe an evolution in specifications where maybe the use of a biosolids compost is required, or a certain percentage of the soil amendments in the specification are required to be recycled?
I mean, it definitely has. I've seen less resistance to it over the years, less specific instances where they're trying to say, do not include this item. So that's a benefit. The internet, as we're all very aware in 2020, is a double-edged sword in the sense that it allows these specifications to be shared throughout companies that are getting bigger and changing. So someone mentioned Tetra Tech before the call. I'll use them as my example. The office in New York might pull the spec from the office in Florida, and that gets used all over the country now in a way that it wasn't previously. I would even say 10 or 15 years ago, where if a spec is useful and works, it tends to grow on its own some. So if we can continue to promote that, I definitely see where biosolids could get further acceptance and more interest by showing that it's worked. Here's a common spec, and not, the stigma will always be present just because of the things we deal with. But I definitely could see some overcoming of that by these nationwide standards and common specifications used throughout large companies.
Okay, great. Well, fantastic. Chuck,
thank you. My apologies again.
No, it's all good. Thank you again for joining us and sharing your presentation and thoughts. Let's see. Just again, a reminder to our participants to use the Q&A feature to continue asking those questions. We'll get to them. I see, Charles, you stopped sharing your screen. So we're going to move on to our next and final speaker today. Rich Nicoletti, who will be presenting on BDP's tried and true agitated bed composting system. And as I've done with the other presenters, I'll introduce Rich via his bio. So Rich is the compost systems manager for BDP Industries. He's been so for the last 7 years. He spent the last 25 years designing and equipping agitated bay type commercial compost facilities, either working for IPS composting systems or BDP Industries. That reference list includes 30 compost facilities globally, composting biosolids, food waste, and municipal solid waste. Rich has a BS in mechanical engineering from Villanova and an MS environmental engineering degree from Drexel. And he is a registered professional engineer in Massachusetts. So with that, Rich, thanks for presenting here, and I'll pass it over to you.
Okay, thank you, Jeff. All right. So, ongoing issues with biosolids, maybe all composting facilities. First and foremost has always been the odor potential. We all know numerous facilities that have closed over the years because of odor issues. Amendment supply is becoming an issue now that I'm hearing about. Where what used to be a waste product, some sort of biomass, is now a commodity sought after for waste to energy or those type of things. Leachate control is now a big thing. I'm aware of at least one facility that was closed in California due to leachate concerns. As Dan mentioned, you have to look at the space available locally versus hauling to a remote site. Weather impacts in the Northeast or wherever they may be. Actually, even in Florida, you get too dry. The CapEx, the capital expense versus the operating expense, and product marketing, which of course Chuck touched on. So my presentation is going to focus on those things that are in the dark, the black text. Other issues which are emerging are the PFAS and what's in the biosolids, but the composting process doesn't really impact those. Okay. So when you talk about how to enhance the compost process, there's really two mechanical ways of doing that. You can either agitate like in a windrow operation, or you can aerate with forced aeration, as in aerated static piles or those type of things. And then there's those technologies that do both, that bring both of those mechanical enhancements in. And those are, of course, in the middle of those two Venn diagram circles. The blue text items are the ones that are enclosed inherently for maximum odor and leachate control. So previous slide gave the text. Here's some pictures to go along with it. Upper right is the aerated tunnel. In the middle is the membrane covered ASP, like Dan was talking about, that they were looking at for Chicago. Upper right is the agitated and aerated bay, which is the technology that BDP promotes. Lower left is Bill's old ASP facility down in Philadelphia. And if you combine that with windrow, you get today what's called turned aerated piles, which is becoming more popular. So just a brief overview of the composting technologies there. All right, what we're seeing is in the biosolids high odor potential world that composting operations are moving towards enclosed type facilities with either agitated and or aerated mechanical enhancements. To address those issues were the issues I had on the Pepe Le Pew slide, and the red text in this slide speaks specifically to that. The bold red text speaks to what an agitated bay technology can do. So being enclosed, it addresses as best as possible odor and leachate. You're bringing in the forced aeration. Technologies use either positive, where you're moving the air up through the pile, or negative, where you're drawing air down through the pile. As Dan mentioned, enclosed systems can operate at lower carbon and nitrogen levels, which means lower amendment needs. Because they're enclosed, you don't need to be at the high carbon and nitrogen range to minimize ammonia generation. When you add agitation to that, you can further reduce your amendment needs, because you're relying on that agitation process to rebuild porosity such that aeration is more effective. Your initial mixture is less critical if you're frequently agitating. As long as you get the proportions reasonably correct, with each agitation, you're going to get homogeneity, which is what you need for a good end product. With agitated systems, you'll end up producing that mature, stable product that Chuck talked about in less time than a static process. Being closed, you've minimized vector and weather issues, of course. Many of these processes or systems can be fully automated. And as Dan did mention, with high mechanical input, you are on the higher end of a capital expenditure with the balance of lower operating expenses, because it's less people sitting in loaders where other mechanical equipment is doing that kind of work. So the bottom line is an agitated system is highly flexible, could take many different type of products and produce a consistent compost. All right, a little background on who we are. The technology started out as basically a sole provider known as IPS. BDP actually produced the agitators for IPS exclusively for like 25 years. When BDP decided to do this on their own, we partnered up with a company called BACT out of Grand Forks, North Dakota. Their expertise is in aeration, ventilation, and odor control. And BDP's expertise is more on the manufacturing controls. Both companies understand composting process, and that's who the technology is being marketed by today, this BDP-BACT joint venture. It's a typical process flow diagram. I won't go into too much detail here, but you're blending your biosolids with your high carbon bulking agent to try and get that right moisture content density feedstock that you want. Run it through the agitated bays, typically for 21 days. Out to curing. At that point, it should be relatively stable such that odor is not a huge issue. So you can go to outdoor curing, and then screening, recycle the unused bulking agent and market the fine compost product. So more key features about our specific technology, the agitated bay. It's a plug flow system. Each batch of material that's put into the bay is assigned a number in our process control system, so we track it through the bay. As the agitator moves up and down that bay, it moves the material from the front to the back of the bay, such that after 21 days, compost comes out the back. While inside that bay, we're monitoring temperature with probes that are cast into the concrete walls that form the bays. We have, of course, forced aeration, either positive or negative. We can compost any organic material. Anything that's compostable can be done with this technology. Like I mentioned, we have the highest feedstock flexibility, fastest time to stability. Not trying to turn this into an infomercial. I want to get to this, which is the original 1980s version of an agitated bay facility. It would have included a 30 horsepower agitator. Each bay was segregated into 4 or 5 zones. Each one of those zones would have had a dedicated blower for aeration and a dedicated temperature probe. Those are single speed blowers. The biofilter would have been a pipe and stone biofilter designed by someone else other than IPS. The ventilation would have been designed by an engineer other than IPS. The method of aeration in the bays was also pipe and stone and was only positive aeration, which means you're pushing that process air into the building cavity and relying on the ventilation system to effectively remove it to the biofilter. The original bays were 2 meters wide. They accepted a 15 cubic yard charge, is what we call. You would have had a mixer, a dedicated mixer in that facility to properly mix the materials to reduce the load on the agitator. And in certain cold climates, we did have facilities that had to add heated. Merrimack, New Hampshire, this facility was built in 1994. It was designed to process about 16,000 tons a year of biosolids on a 6-acre site. The compost building is 42,000 square feet. And you see the biofilter adjacent to it. That's about a 16,000 square foot biofilter. The bays were designed for 21 days retention. The material comes out of the bays and goes into their open windrow curing piles, sits there for another 30 to 60 days, goes to screening, and then the product is marketed. This facility had 3 30 horsepower agitators serving 15 bays. It was the bays had to be loaded with a bobcat or a skid steer because they weren't wide enough to accept a loader. And this was a facility that did use heat addition up front because there's fogging in the building. So during the very coldest days, they would put some warm air in to drop the fog. Now, what we're currently making and what is being applied to new designs. Okay, so first off, the agitator. The agitator has gone from 30 horsepower to 100 horsepower. And the bays have gone from 2 meters wide to 3 meters wide, from 6.5 feet deep to 8 feet deep. We did that in steps. We were very concerned about making sure we could still keep well aerated compost. So it went from 6.5 to 7 to 7.5 to 8. So today we're marketing 8 by 10 bays. Through our partnership with BACT, the building ventilation system, the biofilter, and the bay aeration system is all designed as an integral air movement network, such that we're not relying on an outside engineer who may or may not have composting knowledge to say how many air changes are appropriate for a building. The 15 yard per charge has now gone to 40 yards per charge in these bays. We no longer need a mixer. We're going a dedicated mixer. This agitator is powerful enough to move through the initial dense stuff, just roughly mixed on the floor with a loader. We're using the BACT floor for both the biofilter and the bay aeration as shown in that in the bay. It's a plan. It is able to do both positive and negative aeration. And we're now using one blower across multiple zones of bays, such that you have less installed horsepower, because the zones in each bay should roughly be operating around the same temperatures. So from the BDP side, what we've done to our agitator is we've increased the horsepower significantly, along with increasing the bay size. On the old design, with each agitation, the pile would move back 12 feet. By the time you got to the end of the bay, what started out as a 6.5-foot high pile was 3 feet high, because inherent in the composting process is volume loss. We all know that. So what we've added to our machine is what we call the capacity optimization gate. And as the machine is controlled, it opens and closes a damper on the conveyor that limits the throw of the conveyor at the back end where the volume is lost, and gets maximum throw at the front end of the bay where you're starting out with your initial charge. That 30 horsepower agitator could serve up to 4 bays, and that was about all it could do in an 8-hour day. It could serve 6 bays, and most important here is to look at the horsepower that is available to the bay. Originally, if you took a slice through that bay, the 30 horsepower machine provided 0.7 horsepower for that slice through the bay. Now we're up to 1.25 horsepower for the slice through the bay. So not only are we putting more power in, but we're able to process faster with that added horsepower per square foot. So there's, on the left of this, you see the picture of the capacity optimization gate opening, closing, opened at the loading end of the bay, wide open, closed, dampening the throw at the back end of the bay. Your picture on the right shows recycle and fresh amendment, waiting for a dump truck full of biosolids, and floor mixing by the loader. Like we talked about, BAC-T being able to handle all of the air movement in the system. Picture in the middle here is the BAC-T floor. Those little crates go across the whole width of the bay and the whole length of the bay. Each zone gets a dedicated RTD still, so that we're properly monitoring for PFRP and VAR. Leachate is fully collected if there is any. In positive aeration, there's usually none. Negative aeration, you're going to get some condensate and some leachate. The good thing about negative aeration, where we can do it, is you're drawing all that foul process air directly into the blower and piping it to the biofilter directly. So it's no longer going to the building cavity, exposing workers to, not the greatest conditions. The other great advantage to negative aeration is the ability to capture the heat that's in that process air and reuse it through some heat recovery system to preheat building makeup air in those cold environments. That'll increase building life because you're not putting high ammonia concentrations into the building cavity. And we've just retrofitted a bay in Bennington, Vermont for complete testing of this process. Some schematics showing what BAC-T provides design-wise here. I assume I'm up against the clock, so I'm moving relatively quickly. Here's the BAC-T floor for the biofilter. For those of you that may have pipe and stone biofilters, you understand that you cannot drive on it when you need to change the media. This floor is designed to be driven on, such that when it's time to change the biofilter media, you just scoop it up with your loader, put it in your bays to compost it, and put the new media down. Right, so now going back to that Merrimack case study, I want to compare Merrimack 1994 to Merrimack today with the same capacity going in. We would reduce the building footprint by almost half, going with 6 bays versus the 15 bays. 6 bays at 8 by 10, capable of handling 40 cubic yard charges versus those 15 bays handling 15 cubic yards per charge. We can go at a lower percent dry solids, a higher density feedstock because of that horsepower per square foot that I talked about. The machine, we would need 1 agitator to process those 6 bays in 8 hours versus the 330 horsepower that were originally installed. We'd use loaders to both load the bay and unload the bay, which is a hell of a lot faster than using skid steers, obviously. The biofilter would be less than half in the square footage because of the inherent efficiency gain with the back T floor. And with negative aeration, we would be able to get that heat recovery and use the free heat versus paying for some sort of fossil fuel-based fuel. So I hope I beat the clock there, Jeff. Upper left shows our oldest facility, which is in Fairfield, Connecticut, pretty close to some high expensive real estate, and our newest facility, which is just being turned online in British Columbia, Delta. Thank you.
Great. Rich, thanks. You know, I'm amazed at the evolution in the technology, and I can just imagine where it's going to be, say, in another 10 or 15 years, in the developments that I'm sure DDP is all over in helping our industry evolve. So thanks a lot for presenting and sharing that information with us.
No worries.
You know, I think that's about all the time we have for today's webinar. I want to thank everybody on the panel and certainly everybody in the audience for the questions that we've gotten today. Thanks to Dan, Charles, and Rich. And again to Kathy and Bill and the programming committee for putting this together. As a reminder, the link to the recorded webinars as well as credit certificates and transcripts will be emailed to all the attendees at the end of the MAVA webinar series by mid-August. Kathy's going to share her screen now to show us the webinar flyer. We've got 2 more webinars that we'd like to have everybody chime in on and join in on. Let's see, just in case I don't see them up on the screen. This Thursday, July 30th, new approaches for digestion and optimization. And Tuesday, August 4th, will be our last one on innovation in thermal processes. So a couple of really good webinars coming up. We've had a lot of good ones already. Thanks to everyone again for participating, and in these challenging times, I think the webinar format has been working great. And with that, we'll let you go. Thanks again. Have a great afternoon and take care.